Welcome to another Ask Me Anything event. If you're watching this on YouTube, I invite you to join me live next time. We have these every Saturday at 11 a.m. Eastern, and you can join for free by starting your free trial on quantreasoning.com. How to count the number of divisors for any number. So just to remind ourselves, what are divisors? If I look at the number 12 as an example, the divisors would be 1, 2, 3, 4, 6, and 12. It's all the numbers that 12 is divisible by. Those are the divisors. Another word for that is factors. So sometimes on the GMAT, they ask how many factors or how many divisors does some number have. And there's a way to reason through that, and we're going to need that way in order to solve this question properly. So I anticipate that it's going to take us quite a while to solve this question because we first have to learn about the fundamental counting principle, which is the foundation of all of combinatorics. So we're not going to really learn combinatorics today. We're just going to learn the fundamental counting principle, which is what combinatorics is based off of. And then once we figure that out, we can apply that to counting factors for some number. So I want to start by asking you a question. If you are at a restaurant and the menu gives you 2 options for an appetizer and 3 options for an entree, 2 appetizers to choose from, 3 entrees to choose from. You are going to be choosing one of each. How many different meals could you possibly have at this restaurant? If you have your choice of appetizer from 2 choices and your choice of entree from 3 choices, and you're going to be choosing 1 appetizer and 1 entree, how would you think about that? Exactly. You could say for appetizer number 1, I could match that with 3 different entrees, so that's already 3 meals. And for appetizer number 2, I can also match that with 3 entrees, so that's another 3. So you're right, it would be 2 multiplied by 3 equals 6. That's how many different meals we could possibly have. Now, what if I add to this story also 5 desserts to choose from? So you still have 1 appetizer you can choose from 2 options, 1 entree you can choose from 3 options, and now also you must choose 1 dessert from among 5 options. How would you think then about the total number of different meals you could have at that restaurant? The same logic that we applied to the simpler question can be applied here. That's right. For each of the 6 meals that we already talked about, there are now 5 different desserts that we could match them with. So you could think of it as for meal number 1, for meal number 2, all the way to meal number 6, each of those has 5 different desserts that you could go with. So you'd multiply 6 times 5 to get 30 different meal combinations. And so this is the fundamental counting principle, which says, and you can Google this later if you want, it says that if you have independent decision points, in our case, the appetizer choice is independent from the entree choice, and that choice is independent from the dessert choice, meaning the choice I made for my appetizer won't impact the number of options I have for my entree, and the choice I make there won't impact the number of choices I have for my dessert. All right? So that's called independent decision points. And if you have independent decision points, you can take the number of options in each decision point and multiply them all together to get the total number of possible combinations. So just for one more quick example, when the Apple Watch first came out, you had to choose a size. There was the 38 millimeter and the 42 millimeter. You could choose from among 6 different wristbands. And you had to choose from among 3 different watches. There was the Apple Watch Sport, there was the regular one, and there was a really expensive one that cost like $13,000 or something like that. So 2 sizes, 6 wrist straps and wristbands, and 3 types of watch. And so if we wanted to know, well, how many different combinations of Apple Watch could someone order, it would have been 2 times 6 times 3. So 36 different combinations of Apple Watch. And what was interesting about the launch of the Apple Watch is that you can probably imagine the options for wrist straps that you got with the Apple Watch Sport were very different from the 6 wrist straps available for the $13,000 watch. They're not the same wristbands, but it was always 6. So the expensive watch had 6 to choose from, and the Sport also had 6 to choose from. And that made the decision points there independent of one another, because your choice of watch didn't impact the number of possible wrist straps for your watch. So those were independent decision points, and there as well you could multiply across the number of choices. So that's the fundamental counting principle, and we're going to be using that today. Let's go back to that example of the number 12. And imagine that we want to figure out how many different divisors does the number 12 have. What I'm going to do is find the prime box of the number 12. And again, I have a video specifically on prime boxes, which I'll link to in the description below and above me. The prime box of 12 looks like this. So we now have, well, actually, let's talk about this for a moment. Any combination of the contents of this box would give us a factor of 12. There's the combination where we choose to not use anything. So imagine 2 to the power of 0 times 3 to the power of 0. That's just 1. Is 1 a factor of 12?
Yes.
Sure is. Okay, what about the other extreme? Use everything that the box has. 2 squared times 3 to the 1, that's 12. Is 12 a factor of 12? And every other combination, so we could use just one of the 2's and use the 3, or use both 2's but no 3, or just use the 3 on its own. Any combination, anytime you're using just the contents of this box, any subset of those contents will provide you with a factor of 12. So we have 2 decision points here. Decision point number 1 is how many 2's do we want to use? And decision point number 2 is how many 3's do we want to use? As we're building this subset of the contents of the prime box of 12. But you have to remember, we could choose to not use that particular prime at all. So for the 2's, I could choose 2 to the power of 0, 2 to the power of 1, or 2 to the power of 2. There are 3 different choices that I must pick one of them. And for each of those choices, we have another decision point here for how many 3's we want to use. We could choose to not use the 3, or we could choose to use it. So in the end of the day, I have a total of 3 choices for my first decision point of how many 2's we want to use. And I have 2 choices for how many 3's I want to use, for a total of 6. And we can check that. Does 12 have a total of 6 divisors? Count them. 1, 2, 3, 4, 6, and 12. That's a total of 6 factors. And this is always going to work. So whenever the GMAT is wondering how many factors does some number have, figure out the prime box for that number. Draw out the different options for each decision point. Each decision point meaning each prime, each type of prime in the box. And then multiply across the number of choices in each decision point as the fundamental counting principle tells us to do. So let's try a tougher example. Let's look at the number 2100. So to find the prime box of 2100, I think the most efficient method is to split out the zeros. So you'd call that 21 times 100. And we know that a power of 10 is just a power of 2's and 5's, because each 10 has a 2 and a 5 in it. So if 100 is 10 squared, well, that's 2 squared, 5 squared. That's 100. And 21, that's 3 times 7. So I'm circling all the primes. And now I'm ready to draw the box for 2100. It has 2 squared, 3 to the 1, 5 squared, and 7 to the 1. So the long way to do this is to write down all the different choices in each decision point. I mean, it's not that long. It's perfectly fine to do that. And we add up, or we see how many choices there are in each decision point. So we have 3 by 2 by 3 by 2 equals 36. So that's the answer to how many different factors does 2100 have. The fast way is to say, look, I see these exponents inside the prime box, and I know that each of those exponents almost shows me how many choices we have for that prime. Why do I say almost? It doesn't take into account the option of not using that prime at all. The 0 option is not counted there. So if we add 1 to each of those exponents, then we'd have the number of choices for each of those decision points, and we can just multiply them across. So in this case, we have 2, 1, 2, 1. Add 1 to each of them, it'd be 3, 2, 3, 2. Multiply across, and you get the total number of factors for that number. So let's go back to the original problem and see what you can do with it now that you know all that stuff. Let me just repeat that for everyone. So you're saying it feels like with statement 2, we're going to get different answers depending on whether x is already a multiple of 2 on its own or isn't. And that's some strong intuition. You're right. We're going to explore that and see how we can prove it or see it more clearly, but your intuition was correct there. So you're right that statement 2 is not sufficient on its own because it would lead to different answers depending on whether there already was a 2 in the prime box of x. Let me just point something out here. The less than makes it a bit more complicated, right? I can't just do that fundamental counting principle that we learned earlier, because the fundamental counting principle would give us the total number of factors, including the number itself, but here everything is excluding the number itself. In fact, let's go ahead and do that. Let's change the conversation. So instead of saying less than, it's saying including, and I'm just going to add 1 to the number that's given here. So this is 5 instead of 4, and it's including. And this is going to be 4 instead of 3, and it's including. And now we can use the fundamental counting principle that we learned earlier. Let's go back to the fundamental counting principle and ask ourselves, how do you end up with 5? So I'm looking at statement 1 now, and I'm asking myself, what kind of prime box would lead us to a total number of 5 different divisors? Only 5 and 1. That's right, because we have to get to the 5 by multiplying some numbers. And 5 is a prime number, so only 5 times 1 is the only way to get a 5. What does that mean for the prime box? How many different decision points does that prime box have? We must have got 5 from some prime number to the power of 4. And the 1 is nothing. I mean, one choice means there's no choice at all. So statement 1 implies that we're looking at a prime box that has some prime number to the power of 4, and that's it. That's x squared. The prime box of x squared, according to statement 1, all it has is some prime number to the power of 4, and that's it. This is the only way that the fundamental counting principle would lead you to a total of 5. There's no other way to get there because 5 is a prime number. So when they're telling you how many divisors some number has that are less than the number itself, just change the conversation. Just make it, add 1 and say including the number itself. Or, I've also seen the GMAT use a different trick. It'll say such and such number has this many divisors that are greater than 1. But what about 1? 1 is also a divisor of everything. So change the conversation. Just add 1 to the number of divisors that they gave you and say that's the total number of divisors. You're in charge. And it's a very important attitude. I think we talked about this last time, right? The GMAT doesn't decide for you what the conversation is. You tell the GMAT. You're the boss. And in the case of some prime number to the power of 4, what are the choices? You could not use that number at all. So that would mean 1, right? P to the power of 0 is 1. Is 1 a factor of x squared? Of course, it's a factor of everything. You could use 1 of them, you could use 2 of them, you could use 3 of them, or you could use all of them. So a total of 5 options. And I know there aren't any other primes involved in this prime box, because if there were, then you'd have to multiply your 5 times something, and then it wouldn't be 5 anymore. So that dot 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 is empty. There's nothing there. It's just p to the power of 4. We established that the prime box of x squared is p to the power of 4. Let's go ahead and make an inference now. What does that mean for the prime box of x? P to the power of 2. If x squared has a prime box that's p to the power of 4, then the prime box of x would be p squared. How do we take the square root of a prime box? Let's just look, for example, at the prime box of 36. Here's the prime box of 36. The way to take the square root of a prime box is to take that prime box and split it into 2 identical mini boxes. So in this case, you'd have a single 2 and a single 3 in each of them. And indeed, 6 is the square root of 36. So going back to the original question, and you want to split that into identical mini boxes, each of them would have half as many p's as the original box. And what do we know about p? It's some prime number. If p is some prime number, then p squared will have how many factors? 3. Because you could take p to the 0, p to the 1, and p to the 2. Those are the factors. As long as p is a prime number. I mean, if p is not a prime number, then it has no business being in our prime box. But we defined p as a prime number when we first introduced it. If a number has exactly 5 divisors, 5 positive divisors, then it must be the 4th power of a prime number. How did we get that insight? Take p and q as different prime numbers. And let's test some stuff. Let's say we have p to the 1, q to the 1. P to the 1, q to the 1. How many divisors would you have total with p to the 1, q to the 1? 4. Yep. That's right. What about p squared q to the 1? What about p squared q squared? That's right. You have 3 times 3 equals 9. What about if we had 3 primes in our prime box? Let's say we have p to the 1, q to the 1, r to the 1. It would be 2 times 2 times 2. What if we had 4 different primes? Then would you have 5 divisors? P to the 1, q to the 1, r to the 1, and u to the 1. Imagine each of these is a prime number. How many divisors would this number have? 16. So how on earth are we going to end up with exactly 5 divisors? There's only one way. That's the only form of number that would have exactly 5 divisors, because 5 is prime. So there's only one way to get to 5. If you're told there's a total of 6 divisors, well, that's a different story, right? How can we get to 6 divisors? It could look like this. Right? That would have 6 divisors. But also, this would have 6 divisors. And I could also write p squared q to the 1, but since we don't know what's p and what's q, those are actually the same thing. So there are 2 different forms of prime boxes that would lead to a total of 6 divisors. Either some prime to the power of 5, or some prime squared times some other prime to the power of 1. If the number of divisors is prime, you have a single prime in your prime box. That's right. I had to think about that for a second, but yes. That's right. And please, let's try not to memorize that. Let's just try to understand why that is. And then we'll be able to use that. I find that if I really get why some rule is the way that it is, then I don't have to memorize it. And the reason it is the way it is because if you have a prime number of divisors, and we know that the number of divisors is always a product of number of choices among decision points, but there's a prime number of divisors, well then there's only one way to get to that prime number via multiplication, because that's kind of the definition of a prime number, is that there's only one way to get there via multiplication. It's that number times 1. And if that's the case, then there must only be one prime in that prime box. That plus 1, which, just to remind ourselves, why do we do a plus 1? Because there is the option of not using that prime at all. And that's not counted when you look at the exponent. Like if you have a prime box with 3 to the power of 7, well, there are actually 8 choices for the 3's, because you could not use them at all. You could use 1, 2, 3, all the way to 7. So that's the reason why we do the plus 1. But the fact that we do a plus 1 means that if a prime exists, if there's a prime that exists in a prime box, there are at least 2 choices for that decision point because of the plus 1. There's at least 2, because either you don't use that prime at all or you do use one instance of it. And if there's more than one, then there's more choices. But the presence of a prime in the prime box implies you already have at least 2 choices for that particular prime number, for that particular decision point. And therefore, you'd have to take that into account when you're multiplying across the decision points with a fundamental counting principle. But if the total number of divisors is a prime number, well, there's only one way to get to that number via multiplication. It's that number times 1. But you never have a 1 because of that plus 1. You're going to have at least a 2. So you can't have another prime in that prime box. There has to be a single type of prime with a single decision point, essentially. And maybe I should take this more abstractly and not talk about prime boxes for a moment. Let's go back to the Apple Watch. If you find out that the total number of possible combinations of Apple Watches that you can get is some prime number, say 13, that means there's only one decision point. Because you can't get to 13 by multiplication, other than just 13 times 1. So that would imply that there are 13 choices of just one thing. For example, 13 different sizes for the Apple Watch. But there isn't a style, there isn't a wristband, there's just size. And there are 13 sizes to choose from. Because you can't get to 13 via multiplication.
Yeah, that makes sense.
So that's the inference there. And that's why if you have a number that has a prime number of divisors, then that prime box can only have one type of prime. With what exponent? 1 below the total number of divisors. Why is it 1 below the total number of divisors? Because of that plus 1 for the case of not using the prime at all. So if we go back to the original question, after all that, our big inference for statement 1 was that the prime box of x squared has p to the power of 4, where p is some prime number, and therefore the prime box of x would be p squared. And if the prime box of x is p squared, then how many divisors does x have? 3. That's right. So can we answer the original question, which was how many positive integers less than x are divisors of x? There are exactly 2. So statement 1 is sufficient on its own, and we would eliminate BCE. Statement 2. So now we're not talking about x squared, now we're talking about 2x. And 2x has exactly 4 positive integers that are divisors of 2x. So 4 including 2x. So you have to ask yourself, what kind of prime box would have exactly 4 divisors? The easy one to think about is this one. That for sure would have exactly 4 divisors. But
Right.
yeah, that's another way to get 4. So with 2x, there are actually two different prime boxes that could represent 2x. Now for the first prime box, can you infer the value of p and the value of x? What must p be for the left box?
It's 2.
Exactly. P has to be 2. Because we know p is a prime number. We know x is some positive integer, because they told us that in the free info. So if the prime box of 2x is p cubed, the only way that's possible is if p is 2 and x is therefore 2 squared, or 4. X must be 4 in this case. What about the other case? If 2x is p times q, and where those are both prime, one of them is 2, and the other of them is x. So what can we infer about x from here? X is what? Some prime number. Which prime number? I don't know. So the inference we can make from statement 2 is that x is either prime or 4. Now if it's prime, how many divisors would it have less than itself? 1. And if it's 4, how many divisors would it have less than itself? 2. And that's why statement 2 is not sufficient on its own. If the true prime box of 2x looks like this, p to the power of 1, q to the power of 1, where p and q are some different primes. If they're the same prime, well then that's wrong. If they're the same prime, then you go back to the left box. But if they're two different primes, and you've got one of each, right, p to the power of 1, q to the power of 1, that is a legitimate way to get to a total of 4 divisors for some number, for 2x. Then what that means is that one of them is 2. I don't know if p is 2 or if q is 2, but one of them is 2 and the other one must be x. So either p is 2 and q is x, or p is x and q is 2. The truth is it doesn't really matter. It's symmetric. And then you would say, well, okay, either way, x is some prime number, whether it's p or q. It's a prime number. X is a prime number. And if x is a prime number, then I know how many divisors it has less than itself. Just 1. But the problem is we don't know which of these scenarios is true. If we knew which scenario is true, then we could answer the question. If we knew that x is equal to 4, then of course we can answer the question. If we knew that x is some prime number, that would also be sufficient to answer the question. But I don't know which it is, and they lead to different answers, and that's why statement 2 is not sufficient on its own. Yeah, in S1, all we could infer about x is that it's the square of some prime. So which prime, we don't know. It's some prime number squared. But that was good enough, because any prime number squared will have 3 divisors, based on that fundamental counting principle. And there's a lot of stuff here that people might potentially want to memorize, and I'll strongly encourage you not to. I mean, I've seen people memorize a rule. Any prime squared will have exactly 3 divisors. I've seen people memorize any perfect square has an odd number of divisors. That's a rule. Should we memorize that? There's no need. Why? Because any perfect square you look at is going to have a prime box that looks like this, where A, B, and C are primes. Any perfect square has a prime box that looks like that. How do I know? Because by definition, a perfect square, you should be able to take and split into 2 identical mini boxes and get integers. So this would have half as many, half of whatever that even number was, and half as many as that even number was, and so on. And it has to be an integer. And the only way half of some number is an integer is if that number was even. So these are all even, and when you plus 1 them, you get odd, times odd, times odd, and so on. And if you're just multiplying odd numbers, you're going to end up with an odd number, because a factor of 2 can't just appear from nowhere. If none of the building blocks had a factor of 2, the product won't have a factor of 2 either. So of course the prime box of a perfect square would have all even exponents, and therefore the number of divisors a perfect square has to be odd. So I've seen people memorize that as a rule. I don't think that's necessary. If you understand where that rule came from, then you don't need to memorize it. And if you don't understand where the rule came from, you have bigger problems in the GMAT, right? Because they're going to come up with a question that tests not whether you memorize the rule, but whether you understand where that rule came from. Yeah, that's right. Any perfect square, and of course 25 times 9 is a perfect square because it's the product of perfect squares. And so it will have an odd number of divisors. That's right. There's another way to think about that, by the way. Like, why do perfect squares have an odd number of divisors? Let's take 36 as an example. 36 is a perfect square. But we know that when you look at all the divisors, you can look at factor pairs. So let's look at the pairs. 1 times 36, 2 times 18, 3 times 12, 4 times 9, and finally 6 times what? Itself. So by definition, a perfect square will have some number times itself when you set up the factor pairs. If that's the prime box of 2x, and you know that x is an integer, they told us that x is a positive integer, and you know that p is a prime number and q is a prime number, and they're different prime numbers, we know all of that because we defined it that way, then one of those mysterious primes has to be 2 and the other has to be x. That's the only way. Think about that. I mean, if I write 2 times x equals p times q, and knowing that x is a positive integer, and knowing that p is some prime, and knowing that q is some other prime, the correct inference is that x is some prime number. Because one of the prime numbers would be 2, and the other of the prime numbers would be x. That's the only way this works. If all you got from today was how to find the number of divisors of any number, by getting a box and adding 1 to each exponent and multiplying across, that's great. Or if all you got from today is that the way to take a square root of a prime box is to split the contents in half, because you're splitting the contents into 2 identical mini boxes. Or if all you got from today was the fundamental counting principle. So next time you're at a restaurant with a prefix menu and you want to impress your date, you go, look, there's 3 appetizers to choose from, 2 entrees, and 5 desserts, and 2 choices of wine. So if you multiply all that across, you get the total number of meals you could have. Now, I don't know if it'll impress your date or not, so that there's no guarantee on that. But if I were your date, I'd be impressed. So if you found this video useful, go to quantreasoning.com for a lot more where that came from. You should also click that like button and let me know in the comments below what you'd like me to make future videos about. And of course, if you haven't yet subscribed, go ahead and do that and click that bell below so you get notified about future videos. See you next time.